What can you make with steel? Cars, buildings, bridges, ships. What else? How about knives and forks, fridges and washing machines, food and drink cans, train tracks? Anything else? Try everything else. Yes, everything. Because even if something isn't made of steel, steel will have been used to make it. From paper clips to pipelines, paper to plastics, nothing in this world can be made, moved or manufactured without steel. So, how do you make the product that helps make everything else? Well, the quick answer is you take iron ore, coke and limestone and put it in the top of a blast furnace. Blast air at it until it's hot, very hot, white hot in fact. And out of the bottom you get molten iron, the material from which steel is made. Making molten iron into steel involves removing some impurities, such as carbon and silicon. In other words, it has to be refined, and this is done by blowing oxygen onto it. Other elements are then added to adjust the steel's composition, making it suitable for any one of the thousands of purposes for which it could be used. The molten steel is then solidified before being formed into a suitable, usable shape. Well, that's the quick answer. But now let's take a closer look at each of those processes and the effect they have on the production of steel. Steel is an alloy or metallic mix of mainly iron and carbon. As a finished product, its carbon content is between 0.02 and 1.5%. But to start the production process, we need high-quality iron ore. Iron ore is common in the Earth's crust and contains iron chemically bonded to oxygen. This is mined in places such as the Americas, Australia and Scandinavia, and then shipped around the world to steelworks. Ores are then blended together to produce a favourable mix. This mix is combined with coke and heated to produce the iron-rich material called sinter. Sintering reduces waste and provides an efficient raw material for the blast furnace. Carbon is required for the blast furnace, and this is supplied in the form of coke. To make coke, coking coal is heated in an oven. This drives off volatile byproducts and leaves carbon. Gas produced in this process is used as a fuel, whilst other byproducts such as tar and sulphur are extracted and refined. These raw materials, sinter, iron ore and coke, meet each other at the blast furnace, where they are fed into the top of the furnace along with some limestone. A hot air blast, from which the furnace gets its name, is injected through nozzles called tuyeres in the base of the furnace. This blast raises the temperature in the furnace to white-hot intensity, around 2,200 degrees centigrade. This very high temperature is needed for the chemical reduction and melting of the sinter and iron ore to form a pool of molten iron in the lower part of the furnace, just above the hearth. The limestone combines with the impurities to form a liquid which floats on top of the molten iron. This is known as slag. The molten iron is tapped from the furnace and the slag skimmed off and taken away for use in other industries, such as road building or cement manufacture. The molten iron we get from a blast furnace, or hot metal as it's known in the industry, isn't pure iron and contains the elements carbon, sulphur, phosphorus, manganese and silicon. To make steel, these elements must be removed or reduced and other elements added, depending on the type of steel being made. The carbon content, at about 4%, makes iron very brittle and unsuitable for rolling or forging, and although iron can be used for castings, most of the iron produced is for processing into steel. Basic oxygen steelmaking, or BOS, is the main bulk production process for refining iron into steel. BOS vessels can take up to 350 tons of molten iron at a time and convert it into steel in less than 30 minutes. First, scrap steel is put into the vessel. And then the hot metal is added, which may have been pre-treated to remove elements such as sulfur. A lance then blows high-purity oxygen onto the hot metal at about twice the speed of sound. The oxygen combines with impurities, and this oxidation produces heat. The temperature is controlled by the quantity of scrap steel and also by the addition of iron ore as a coolant. The oxidized carbon creates carbon monoxide gas, which can be collected, cleaned, and used as a fuel. The other oxidized impurities combine with lime that has been added during the blow to form a slag. The quantities of scrap, hot metal, ore, lime and other substances are calculated to ensure correct temperature and composition of the steel. Refining can be assisted by injecting argon, nitrogen or oxygen gases through the base of the vessel. And a sublance is used to measure carbon and temperature during the blow to allow final adjustments to be made. During tapping, alloy additions are also made to adjust steel composition. By this stage, the carbon has been reduced from around 4% to about 0.05%. Finally, the vessel is tipped to remove the slag for recycling. The other main method of making steel is by means of the electric arc furnace, or EAF as it's known. The EAF process predominantly uses cold steel scrap, making it one of the world's largest recycling processes. EAFs make up to 150 tons of steel in a single melt in less than an hour. The furnace is filled with recycled steel scrap. The roof is then swung into place and 3 graphite electrodes are lowered into the furnace. A powerful electric current is passed through the furnace. An arc is created and the heat generated melts the steel scrap. Lime and fluorspar are added and usually carbon and oxygen are blown into the melt. As a result, impurities in the metal combine to form a slag. The steel is sampled and analysed, and once it reaches its correct temperature and composition, it is tapped off. At this stage, final adjustments to precise customer specifications can be made by adding alloying elements. These furnaces give very precise control over composition and are used for producing a variety of special steels, including alloy steels and stainless steels. Many bulk steels are also increasingly made by this route, and it's expected that EAF output will account for half the world's steel production within a few years. Small steel-producing plants operating with EAFs closely linked to casting and rolling facilities are often referred to as mini-mills. These can produce relatively low volumes of specialist products. Mini-mills are often situated very close to where these products are most in demand. After the BOS or EAF steelmaking processes, a combination of secondary steelmaking processes is used to further refine the steel. These specialist processes are designed to improve the consistency of temperature and composition within the steel. They allow the removal of gases such as hydrogen and the reduction of elements like sulfur and the addition of alloys and slags. All of this ensures the steel meets exact customer specifications before casting. Continuous casting is the process used to solidify the molten steel ready for shaping. A ladle of steel is teamed or poured through a gas-tight refractory tube into a tun dish. This is a reservoir and feeds the steel through further gas-tight refractory tubes into a number of water-cooled copper moulds. The flow rate is controlled, and with only the outer shell solidified, the steel is drawn from the bottom of the mould through a curved arrangement of support rolls and water sprays. It then emerges horizontally as solid steel strands and is cut to length by automatic gas burners. Depending on their size, these solid shapes are called billets, blooms and slabs, and are now ready for shaping into finished products. Sections, rails, rods, wire and bar, tubes and plates, profiles and strip. Our finished products are the raw materials for thousands of other industries. Although forging and extrusion can be used to shape steel, we are mainly going to look at the principles of steel rolling. Steel is highly resistant to shaping when it's cold, and for that reason it's generally rolled whilst it's hot. To make sure the steel is at the correct temperature for rolling, it's fed into a furnace. Here it travels through several temperature control zones until it's at the correct temperature and ready for rolling. Whatever the product, the principles of hot rolling are the same. Steel is squeezed between rolls until the final thickness and shape are achieved. To do this to steel, the rolls must exert forces of tens of millions of newtons, equivalent to the weight of thousands of tons. So the rolls run in massive bearings mounted in housings of great strength and driven by powerful electric motors. These are known as mill stands. Layouts of rolling mill arrangements vary from a simple single stand to several stands either side by side or in a line. The rolls themselves can either be plain for flat products such as strip for car panels or profiled for sections and bars such as beams for use in construction. Mill stands have various roll arrangements depending on what product is being rolled. The simplest arrangement is a two-high stand, and these are mainly used for long products, such as sections, piling, rails and rod rolling. For light sections and bars, three-high stands are sometimes used, with the steel passing one way through the back through the top gap. Four-high stands have two work rolls in contact with the steel, supported by larger backup rolls to prevent distortion caused by the rolling face. These give greater accuracy for rolling flat products. Universal beam mills also include stands with both horizontal and vertical rolls bearing on the steel simultaneously. Rolling processes are computer controlled. They're monitored up to 50 times per second and measured to an accuracy of plus or minus 50 microns. The rolled steel is then cooled in a way appropriate to its end use and prepared for further processing or dispatch. One of the further processes is cold rolling of strip. This is used to produce a thinner, flatter product than is possible on a hot mill, down to a thickness of 0.15 millimeters. Forming properties and surface finish of cold rolled strip is better. It can also be coated. with zinc to protect it from corrosion, with tin for cans, and with a plastic coating or paint for protection and decorative purposes. There are two types of steel tube, welded and seamless. For welded tube, the basic principle is to take flat steel strip or plate and form it into a cylinder, either by rolling or pressing before welding the edges together. To make a seamless tube, you must first bore a hole through a hot billet, either in a large press or by rolling the billet through special piercing rolls. The hollow billet is then stretched over a bar, which enables the interior of the tube to be sized. For both types of tube, a final sizing operation can take place, slightly reducing the outside diameter to the required dimensions. So, these are the processes used to manufacture steel, the world's most versatile material. To ensure efficient, safe operations and the production of quality steels, each of these processes use sophisticated computer control and skilled operators. Complex logistics support steel manufacturing and the distribution of finished products to customers around the world. To meet the needs of those customers, there are thousands of different types of steel, each with different properties, making them suitable for thousands of different uses. But it doesn't stop there. New steels are being continuously researched and developed to offer ever better properties to meet ever greater demands. And every year, almost 400 million tons of steel, around half of the world's total production, is made from recycled steel, making it the world's most recycled material. From the Earth's crust comes the iron ore, to make the iron, which makes the steel that shapes the world.